Hello everybody, my name is Ritesh Ahuja and today we are going to look at a demo of Bayun. First of all, what is Bayun? Bayun is a trustless SDK to enable enterprise SaaS applications protect their customer data, especially any data of sensitive nature. Now, what do we mean by trustless? It means that the SDK does not rely on any trusted server or infrastructure whatsoever to enforce these data protections. And we do not trust any privileged humans either. And we'll see in a bit how it's superior to zero trust as well as end-to-end encryption, even if used together. So we're going to see today's demo of a very simple video conferencing application. And the reason we chose this use case is because of the mess that Zoom got into during the early days of the pandemic. They had to spend around $100 million or so to fix a part of the problem that Bayun is trying to tackle. That's why we built a similar demo app just to showcase the superior capabilities of our underlying SDK. So let's go look at the app itself. So I'm going to log in here as user one and then start a new meeting. And then I'm going to add a couple of participants to it. User two and let's say user three. So again, what we just did was created a new meeting with user one being the host and added user two and three as authorized participants. Now let's go back and look at how these steps would be implemented in a typical video conferencing application, or rather any SaaS app in general. So user one created the meeting. Let's say data A, contents are encrypted with key A, and the access to data is governed through a policy table. So here data A says user one. Now when user one shared data A with user two and three, the entry in the policy table for data A got updated to include user two and three. Everything else remains the same. Now a little later, user 2 comes in to access data A, which we'll also see in the video app. At that point, user 2 has to first authenticate with the authentication service, which could be a separate independent service like Okta. Once the authentication check passes, the authorization service does a check in the policy table. And if that also matches, key A is used to decrypt data A and release to user 2. Similarly, user 2 and 3 could have their own data B and C encrypted with their own keys and corresponding entries in the policy table. The main thing to note here is all the keys are gray and controlled by the authorization service itself. In fact, the authorization service could choose to use a single key to keep all data encrypted. Now, the fact that we are using two separate trusted services for authorization as well as authentication makes the system vulnerable to a bunch of threats. First of all, some selected limited privileged admin employees of the SaaS service provider itself can access all keys and all user data. Similarly, some privileged admin employees of the infrastructure provider like AWS, Azure, etc., where the backend of the SaaS service is executing, they can access user data. And the enterprise IT admins of the organization whose employees are using the service could access the employee data. So now, one big issue, of course, is that any of these admins could become malicious themselves and mount what's called an insider attack. But the other issue is they could be hacked, and a hacker could use the taken over account of a privileged admin to breach the system. Or any of them could be compelled or forced to share data with a malicious entity like a rogue government agency. And that's exactly what the issue was in case of Zoom calls being routed through servers in China, where either infrastructure admins or the service admins being employees of Zoom in China could be forced to share user data with the Chinese government. And of course, the fact that we are running these trusted services, hackers could exploit any bugs or vulnerabilities in the code of these services to make them act as agents of the hackers and access the user data on behalf of the hackers. And the same three tiers of threats apply not just to the authorization service, but also to the authentication service as well. For example, a hacked Okta admin account could be used to fake login as user one say and force authorization service to release all data belonging to user one. And of course, we all know that Okta was hacked multiple times last year alone. So obviously, this is a total mess. It's almost like going to a bank to rent a safety deposit box, and the bank manager says that you are not going to get your own individual key to your locker. It's the bank manager who controls all the keys. And the bank manager himself relies on a trusted doorman to check your ID and tell the manager which key to release to you. And on top of that, the property manager of the building where the branch is physically located, he can access any locker anytime he wants. Now, of course, any of these managers themselves could become malicious, but they could also be robbed or they could be fooled. For example, the doorman himself may actually be an employee of a separate service company altogether. And he would have his own chain of commands with his own manager, etc. And any of those could compel him to fake your ID and pretend to be you and pick up your key from the bank manager and use that to access your locker. So no wonder that breaches keep happening and things keep getting worse and worse. That's why Bayun is trying to solve this problem. And how do we solve it? In two major steps. First step is when user one creates data A, they actually deposit an encrypted key with the server such that only they can control this key through the secure enclave of their end device. So this is somewhat similar to pass keys, where a secret key on the end device is used to authenticate the user. The main difference here is that secret key is actually used to decrypt all the data that belongs to that user. Similarly, user 2 and user 3 control their own data with their own keys and not with a trusted services key. So in this way, this is also similar to Apple's keychain. In fact, Apple's own implementation of passkeys relies on keychain itself. Now, the second big change is when user 1 shared data A with user 2 and 3, user 1 himself created two more copies of key A and encrypted each one individually for user 2 and user 3 to control respectively. So this is how we make sure that every user gets their own key to the bank locker. Now let's go back to the demo app itself. So here user 1 is in room 319 and we are going to log in as user 2 and join room 319. So now that user 1 and user 2 are having a secure meeting, let's go back and look at how things worked a little differently here as well. When user 2 came in, at that time, besides going through the standard authentication checks, they also downloaded all the purple keys belonging to user 2 locally on the end device and decrypted these keys locally to store them in the secure enclave. And it's key A2, the key for data A belonging to user 2, that enabled user 2 to join the meeting, not a simple check in this policy table. And note that no authorization service or no admin has access to any keys whatsoever. In fact, if we go back and try to join this as a malicious admin, same room, or a hacker, what they will see is garbage because they do not have access to any decryption key of the meeting. So this is how we make sure that the system is protected at least from both server-side infrastructure issues as well as communication infrastructure issues. So these two levels of threats have been protected against. Now, next step is to see how we protect against user-level threats, especially the case of new device onboarding without getting a trusted enterprise admin involved, because usually that's the most challenging use case. I'm going to log in here as a user. who has never logged in on this device before. So in this case, we see that the user is prompted with 5 different questions, and these questions were chosen by the user themselves at the time of registering their account. Now, what's going on here is all the 5 answers are cryptographically combined together to generate the secret key of the user for them to be able to decrypt all their data. And at least 3 answers have to be correct for the user to generate the correct secret key. And nobody knows how many answers are correct or which answers are correct. So it gets much harder for a hacker to now guess at least 3 answers together, because nobody can guess these different answers independently. But let's say even if the hacker does manage to get at least 3 answers correct, next they will have to go through a facial recognition check to make sure it's only the authentic user who can get it. And even the fingerprint of user's facial image is kept encrypted on the server with a key that the user themselves control. So this makes sure that there are no privacy issues with using facial recognition. First of all, we don't store the facial image itself. We just store a fingerprint of that, and even that is kept encrypted in a way that nobody other than the user can access it. So even if there is a breach or a malicious insider attack, basically no harm is done. So this ensures that we take care of threats at all 3 levels and the service becomes completely trustless. Now that every user controls their own data exclusively with no admin access whatsoever, not even enterprise admins, how do we ensure that if an employee is using some data on behalf of their employer, how is the employer protected when the employee gets hit by a bus, or when a disgruntled employee leaves the company without voluntarily handing over access to data back to the company? The way we solve this problem is by distributing admin controls across multiple admin employees of the company. So any company can have n designated admin employees, out of which they can configure that at least k admins would have to approve any such transfer from one departed user to another employee. So in this case, I'm going to start a transfer from user 5 to user 4. And in this case, there are total 3 admins in the company, and at least 2 have been configured to approve any such transaction. So 2 approvals are required. One has already happened. It was a transaction initiated by user 1 admin to transfer data from 5 to 4. It is in progress. And any of the N admins can decline this transaction. So basically, this is a transaction happening transparently in front of all the N admins, such that at least K have to explicitly authorize it. So it's sort of similar to the blockchain concept, where transparency being combined with multiple approvals is what makes things happen cryptographically without relying on any single trusted server. So let's go to the other admin account. Here we'll see a pending transaction waiting for this admin to either decline or accept. So let's say everything looks okay. This is a transaction in progress, and the second admin also accepts it. Now this transaction is fully approved, but it's pending acceptance by the new owner. Till the new owner accepts it, again, any admin can decline it. So if a hacker were to try to exploit this system now, to try to get access to any employee data, they would have to hack into at least K admin accounts, and those admin accounts are themselves protected with secure enclaves of their end devices and their own facial recognition checks, etc., etc. So it becomes much harder, especially because any of the remaining N can also get suspicious and decline the transaction. Similarly, if admin users themselves were to become malicious, at least K admins users would have to collude together. So not only we have made the system completely trustless across all 3 levels, but also taken care of enterprise controls. In fact, we can take an arbitrary enterprise policy and convert that into cryptographic encoding of keys such that the policies now are now embedded into encryption itself of the data, and policies go with the data wherever data goes. And once we have these policies embedded into encrypted data, you can throw it on Twitter with absolutely no controls whatsoever, and the policies are still enforceable. So this is the real breakthrough, which ensures that this model is far superior to zero trust and end-to-end encryption. And as far as we know, nobody else out there has such a completely foolproof model available. As we can see in this table comparing Bayun with some of the other popular solutions in this area. So some of them do solve the authorization problem to a large degree, but they are really lacking in other related areas, especially so in enterprise administration, where Bayun really stands apart. So this concludes my 3 demos. Any questions?